All right, good afternoon. It's really a pleasure to be here. Thank you to Chelsea and to Amber for the organization and for the invitation to speak to you guys today. And to tell you guys a little bit about some of the work that we're doing in our lab, specifically when it comes to the idea of making faces. And it's been a really nice introduction by Elizabeth, and I think I'd like to try to build off of that a little bit. So when you think about making faces, I think for us, the inspiration in terms of thinking about faces is that the face is really an important part of our body, right? So when you think of other people or other people think of you, most of the time you're picturing the face of that person. And if you're thinking about your ID cards, your driver's license, your passports, or whatever it may be, again, it's always the face you're taking that image of, right? So that image of the face is really important to our identification. It's also, for each person, is really important for how we see ourselves, right, for our sense of self. And so trying to think about how that face matters, we could look at this supermodel. Anybody recognizes this supermodel? Yeah, a few of you are dating yourselves by recognizing the supermodel, but that's good. All right, so this is Grace Jones, right? So she's a supermodel in the 70s and 80s. And she was famous because sometimes she had this really outrageous way of dressing, sometimes some outrageous hairstyles. This is one of her most toned down images that I've put here. But you could also see, so certain things stand out in this image, right? So one is the fierce look that she has on her face. But I like this image because it speaks to, if you look at it, you could see a lot of things here in terms of her facial structure, right? You could see her nice forehead, right? That very prominent forehead, prominent cheekbones, the square jaw, her pointy chin. Right? And all of those aspects of her facial features are depicted by her facial bone, by the underlying bony structure there. So when you think of our sense of self, then that underlying facial bone is actually an important component in terms of our sense of self. So if that becomes damaged, then it's also going to damage the way we see ourselves, the way others see us. So we could think about that in the context, for example, of this patient. So this patient had a cancer that metastasized to her midfacial bone, and that bone had to be removed, resected. And you could see a lot of the changes in her facial structure as a consequence of that bone being removed, right? So you can see her eye is drooping. You can see how her nose is indented inside of here. And to some extent, you could also see the fact that her face on that left side is a little bit sunken in compared to the other side of her face. So that happens because she's missing a lot of that bone, and someone like this is actually going to need a bone graft. The important thing, Chelsea put up some numbers at the beginning. The important thing is that this is not an individual, it's not in an isolated case, because each year there are about 200,000 patients who are going to need a bone graft to replace something within the face. This is just in the US. And if you think about other bones in the bodies, this goes up a lot. So how does the bone structure of this patient look? So we can see that here, right? So the patient is actually missing this large chunk of bone right there. And that explains obviously that facial structure. So if you look, there's no orbital floor, so her eye is going to fall down. She's missing a piece of the nasal bone here, and therefore her nose is sunken in. And of course, if there's no bone underneath her face or skin, then her face is going to sink in that region as well. Right, so someone like this is going to require a bone graft. And you want to think about this, how is the size of this important in terms of thinking of that regeneration process? And we all know size matters, right? So if it's just a fracture, that fracture is going to heal on its own. Many of us have had fractures in the past. But because this piece of bone that's missing is so large, and when we say large, what are we talking about? Not to be flippant about it, but I wanted to put something that people have a sense of what is that size, right? It's really not, we call it large, but it's really just something in the size of an Oreo, or maybe just a little bit bigger than that. And so the question is for many of us here, why is that so difficult to regenerate? I mean, think about the technological advances that we have now. Why is something that's this size so difficult to regenerate? What else have human beings accomplished that should make this look very simple? So think about this. This is what we've accomplished, right? We have built this bridge. It's just part of the bridge. This bridge is 26 miles long. This bridge has been built over an ocean, right? So we've been able to accomplish this by building a bridge 26 miles over an ocean. But even this is not one of the major accomplishments of the human race, right? There are some things that we could scale up much more than this. So let's scale up a little bit. So we could think about the solar system, right? So you guys probably recognize this schematic of all the different planets here. And a couple of them I want to draw attention to. So there's Earth, and here's this guy, planet, small dwarf, whatever you want to call it, Pluto, all the way out there. But it's really far out there, right? So it's not drawn to scale. So if you think about the scales, this is about 100 million miles from the sun to the Earth. And this really should be about 50 times longer than that, right? So that, if you were to really draw this to scale, Pluto would be all the way out into the other room somewhere like that. Yet we've been able to take something like this little satellite, which is about the size of a car, and send it from Earth all the way to Pluto, take images, and send it back to Earth. Right? So again, we've done things on a significantly larger order of magnitude than healing bone. So again, if you were to return to this, why is something like this so challenging? And what do we do right now as the best case scenario? The best case scenario, we found that we can't do anything, in spite of, you just heard Elizabeth's talk, we can't do anything that's better than the native bone. So what we do right now is to take this native bone, something from some other part of the body, and simply to go and use that and replace it to regenerate that bone there. And this is what that looks like after a period of time. Right? So you've taken that leg bone, non-load-bearing leg bone, and you've broken it up into different pieces. So now it looks a little bit like a puzzle, and you've tried to use that to regenerate this facial structure. But it doesn't take an engineer or orthopedic surgeon or a plastic surgeon to see that this doesn't look anything like the next other side of the face. And so for all cases that the underlying bone structure is actually going to impact how your facial structure and your ability to interact in society, then this is actually something that's significantly, it's a little bit primitive if you think about it. Right? So we just saw an example of the ancient Egyptians who would actually do prostheses. This is a little bit primitive as well. So what we're trying to do in this case now, we're trying to harness the power of tissue engineering to do that. And tissue engineering, as many of you will be aware, there are a few components. Right? So the first component we look at is the scaffold. And this has been introduced already, but the idea of the scaffold has essentially three functions. The first function would be that it has the shape of that piece of bone that we're trying to regenerate. So by having the overall geometry of that, we could control the structure of the new tissue that's forming. The other component of this scaffold is that it should be porous, and that porosity is important. It's going to allow cells to grow into the spaces. It's going to allow blood vessels to grow into those spaces. It's going to allow nerves to grow into those spaces. Right? And all of those things growing in are going to help to regenerate that tissue that's been missing from there. And then the third really important component of that scaffold is that after all that tissue grows in, this should disappear. So it should dissolve away. So what we could be left with is actually just this native bone structure. For it to do that, that scaffold is usually combined with stem cells. In our studies, in the studies we do in our lab, those stem cells, we get them from fat tissue, right? So those stem cells are something the important part of stem cells is that they can become different types of cells within the body. And even though we're trying to get bone tissue to form, we could take those stem cells from fat. So now you could feel a little bit better about yourselves every time you have that McDonald's burger and that shake. You actually start to replenish the stem cell source. But those stem cell source then needs to be, because it become anything, it's really important then to tell it what to become. And so what we do with this is to provide certain cues for it. So for us, we provide with certain signals that tell those stem cells they should be forming bone grafts or new bone. And we can do all of this outside of the body. We've done all of this outside of the body. Doing all of this outside of the body, we can create these bone structures. So this is the joint of the jaw, right in front of the ear, allows me to talk, allows me to eat, etc. We can make this joint. But if you could do this outside of the body, our next goal, obviously, is can we do this inside of the body? We do this inside of the body, obviously, we start to think about this using animal models of it. And the animals that we start with and we use primarily are mice. So since mice are really tiny, have really small faces, what we do most of the time is to cut out a piece of the bone, of their skull, a circular piece of the skull and see whether we could regenerate that. So that circular piece of the skull is a little bit like the patient's bone that was missing. It's not going to heal on its own. Even though it's small, it's large enough that it's not going to heal on its own. And we want to see if we can put in these different components then to start to regenerate that within a mouse. And we've done this, and you can see here, so this circle will represent the little circle that we've cut out from it. And if we put our scaffold only, we start to see some, the beginning of some regenerative response where bone starts to grow in from the outside into these regions here. But even if you leave it for a long period of time, that bone doesn't ever fully regenerate in that space. If we add certain bone cues to that, it gets a little bit better, right? So once you start adding those bone cues, you can see a little bit more regeneration inside of here, more bone growth around the edges and in the central regions of it. And once you put stem cells inside, then we get a significant amount of new bone regeneration. So now we can get over 90% bone regeneration inside of these what are called critical size defects, defects that are not going to heal on their own. So that's the idea that we take, and we want to use this within patients. So the idea to go from scaffolds to patients, obviously we start with some sort of imaging. So that same 7 medical imaging that we started with before, we can get the image of any piece of bone, and using technologies that exist now, we can make any scaffold with any of that shape, right? We can control the overall shape of that scaffold. We can control the internal structure of that scaffold, of the pore spaces that allow bone to ingrow inside of there. And the way we combine it with everything else then is that what we'd like to do is to have those bone signals actually incorporated into the scaffold itself. The idea behind that is that if we can have those bone signals incorporated into the scaffold, then all we need to do for the surgeon is to just give this surgeon, when the surgeon has this patient on the operating table, we can simply provide them this scaffold in a sterile packet. Right? They can take it, remove the patient's stem cells at that point in time. So it's essentially what I call a point of care approach. Remove the patient's stem cells, put it in the scaffold, and immediately implant it back inside of that patient. And so we've been testing this, going from mice and now to pigs. All right? So here you can see, obviously, it's a team of people now that work on this. It's not us by ourselves, even though we're engineers, we work with material scientists, with imaging people, and here with a team of surgeons. And you can see this surgeon at the back is actually now sewing up where she made an incision and took out some fat from this pig. Whereas these surgeons in front here are actually working on the face of the pig here where they're trying to regenerate that bone, where they're implanting that scaffold, and we're injecting those cells back inside of here. And so this is our goal, this is our approach, and I think what we hope to do to accomplish using this is actually to start changing the lives of people who matter, right? So we want to go from this stage of what we've done in the lab and hopefully really get ourselves to the stage of working with patients like this and patients like that the one that I showed you earlier. Thank you.